Good afternoon, physics friends, and welcome to Chapter 5, which I have entitled Forces in Two Dimensions. This is the first chapter of quarter number 2 for you, and we're going to be talking about what happens when you push or pull, or you are moving, or you've got velocity in 2 dimensions. So how do you, if you're pushing on something this way and then you push this way, or if you walk this way and then you walk that way, how do we handle that? And I just wanted to get us started today with a cute little video. It's of a plane landing down in, oh gosh, in Spain. Very crazy. This is vector addition at its finest. And a vector, if you can remember, a vector is something that has a magnitude and the velocity. So, I'm sorry, a magnitude and a direction. And we know 4 things to this point that have both of those qualities. Displacement. I move 5 feet in this direction. Displacement is a vector quantity. Velocity, I can have velocity in this direction or this direction, positive or negative. Acceleration, and also forces. So all 4 of these things, if they have a magnitude and a direction, you have to add them. It depends how big they are, and it depends on what direction that they're acting on when you're doing something. Like this plane right here, classic example of vector addition, where the plane, it's pointing in this direction, but the wind is blowing it this direction, so it's actually traveling in this direction. The way it's pointing plus the wind equals the actual. And when we take vectors, we're going to always add them tip to tail. So this is the thrust force provided by the airplane is the blue one. The green would be the wind. You add those 2 together, you get your actual direction of motion. And that's how vector addition works. Now, in order to do vector addition, you're going to have to first have a pretty good handle on sine, cosine, and tangent. And it just bears me repeating that sine, that's SOHCAHTOA. The S stands for sine, the C stands for cosine, and the T stands for tangent. The O is opposite, the opposite side. The H is the hypotenuse. And the A stands for adjacent. So when you've got a right triangle, and this only works, my friends, in right triangles. If you've got an angle here, the opposite is going to be this one. The adjacent is going to be, you might think to yourself, both of these could be the adjacent, but it turns out that it's actually the bottom one. It has to be, because this one is the adjacent, because this one up here is the hypotenuse. The longest side of a triangle is always going to be the hypotenuse. So here we go. I'm going to do 3 quick examples, and I'm going to put this sine, cosine, and tangent to work. So the first thing I've got is I've got a person. They're walking 15 kilometers south. They turn 90 degrees left, and then they're going to walk 25 kilometers. How far are they from home, and in what direction do they need to walk if they wanted to go home? So here we go. I'm going to draw a picture. The person walks 15 kilometers south. They turn left. Now you got to be real careful. When you look at this, this looks like it's the right, and then this looks like it's the left. from your perspective. But when you're walking south and then you turn left, turning left is actually this direction. That's left while you're heading south. You have to have that spatial awareness when doing a problem like this. And you walk 25. So I'm actually going to make this a little bit more to scale. 25. How far are they from home, and in what direction do they need to go if they wanted to go home? So here they are. The question wants to know how far are they from home. In the vector world, we call this the resultant. The resultant is the sum of one or more vectors acting on a body. So if you have a displacement of 15 south and then 25 going at a right angle, that tip to tail, adding the vectors tip to tail, gives me the resultant. This is going to be the Pythagorean theorem. Because I've got a right triangle here, this is very nice. All I do is I go 15 squared plus 25 squared. That's going to equal my resultant squared. So just doing a little bit of math, 15 squared is 225, 25 squared is 625. I add those things together and then I take the square root of it. It ends up being 29 kilometers. Now, what direction would I want to walk if I want to go home? I'm looking for this angle. Let's call it theta. What I'm going to do is I'm going to use the tangent. I like using the tangent because I'm already given the 15 and the 25, and this 29 is kind of rounded. So I'm going to say the tangent of theta. Tangent means opposite, 15 over 25. That's that whole SOHCAHTOA thing that we just did. Tangent, opposite over adjacent. And the opposite is 15, the adjacent is 25. Now to move the tangent over, what I'm going to do is I'm going to divide both sides by tangent. So I do the tangent to the negative 1 power. 15 over 25. So I just pull my calculator out to do this part of it. You have to make sure that when you're using sine, cosine, and tangent that your calculator is in degree mode. It's really, really important because if it's not in degree mode, you're going to get the wrong answer. So you want to go to the mode key, make sure it's in degrees, and to do the inverse tangent, it's second function tan, and I get that inverse tangent, 15 divided by 25. And I get 30.96 or 31 degrees. So this is 31 degrees. Now you got to be really, really careful. This is 31 degrees north of west. So it's 29 kilometers at an angle of 31 degrees north of west. That's if I'm trying to go home, this is west, and I'm going north of it. I could also use the angle right here. This angle right there is going to be 59 degrees. That's going to be west of north. So here's north, and I'm measuring west of it to get this angle. 59 degrees west of north or 31 degrees north of west. Both of them are acceptable answers. I'll do a couple more examples of this if it doesn't make sense to you right now. Here's another one. A plane flies at 15 kilometers per hour and it's pointed straight south. There's a wind blowing from 45 degrees east of north with a speed of 25 kilometers an hour. What's the direction and with what speed does the plane fly from the ground's perspective? Now, this problem, even though it's dealing with speeds, actually velocities, and this problem right before it, it's dealing with displacements. These are all vector quantities, so I treat them all the exact same. So there's a plane. So I'm first of all going to draw a plane from above it. So here's my plane. It's got a propeller on it. And it's pointing straight south. And its airspeed, it says its airspeed is 15 kilometers per hour. There's a wind, and it says this wind is blowing from 45 degrees east of north. So if this direction is north, and I'm going to measure east of it, 45 degrees. So the wind is blowing like this with a speed of 25. What direction and what speed does the plane actually fly? So this plane, even though it's pointing itself south, it's going to get blown this way by the wind. So here's how you do this. You just add these vectors tip to tail like so. And this, it gets a little bit tricky, but I'm going to show you how to deal with a problem like this using sines and cosines. So here are the steps that you're going to do when you go through any problem like this. A problem that's got diagonal vectors is what I mean. The problem right before it was pretty straightforward because I only have vectors going left and right and only vectors going up and down. You'll find that the end of my problem I'm about to do is exactly like the problem, this one right here, number 1. So the first thing that you're going to do is you look for diagonal vectors. I have a diagonal vector in this case. It's the blue one, 25 kilometers per hour. You break this x and y components. I'll show you what I mean. I'm going to break this vector into its x and y components. I'm just going to copy this real quick over here. 25 kilometers. And I know that this angle, well, let's see, just wait 1 second. I'm going to break it into its x, and I'm going to then break it into its y component. Like that. I know that this angle is 45 degrees from a little bit of geometry that I did at the very beginning. I had said that this was 45 degrees east of north. So when I put this down here, it's kind of that same triangle. When I bring this over here, that same 45 degrees is right there with a little bit of geometric proof. Put that back. Put this back. So I'm going to use sine and cosine to find those components. This x component, the horizontal component, and the y component, which is the vertical component. So what I'll do is I'll say the sine of 45 degrees. If you remember, sine is the opposite over the hypotenuse. Opposite is y. The hypotenuse is 25. So I go to my calculator and I take in 25 times the sine of 45. And I get 17.7. Or I'm just going to go with 18 right now, because I think I've only got 2 significant figures in this thing. Yep, I'll just roll with 18. Because this is a 45, 45, 90 triangle, this is also going to be 18. I can skip over. I could use the cosine. But it's going to come out to be the exact same number. Step 2. Replace the diagonal vectors with x and y components. So this 25 kilometers per hour, what I'm going to do, I'm going to replace it with this one and this one. It's a little bit muddled, but I'm going to take that one away. And now, if you'll notice, I have kind of a right triangle. I've got a leg right here, and I've got a leg right here. So I can have my resultant. Brings me to step 3. Add all horizontal and vertical components together. So I'm going to do it up here. This is step 3. And I do it with a really engineering, math speaky type thing. I do this. I say add up all the forces. I'm sorry, not forces. In this case, these are velocities. Add up all the velocities in the x direction. There's only one in the x direction, and it's negative 18. Add up all the velocities in the y direction. Negative 15 plus negative 18. Negative being down. So negative 15 plus negative 18 comes out to be negative 33. So what I've got, I use the Pythagorean theorem to find the resultant. So what I have is I've got a big right triangle where this is 33, this is 18, and then I can use the Pythagorean theorem. A squared plus b squared equals c squared. I already did that kind of before I came here, and that comes out to 37. That's how fast this is going with respect to the ground. We call that ground speed. It's going 37 kilometers per hour. And then what angle is it actually going at? That's this angle. I'll call it theta. I'm going to then use the inverse tangent. So step 5, use inverse tangent to find angle. So I'm going to do the inverse tangent of 18, because the opposite is 18, over the adjacent 33. So when I run that through on my calculator, it comes out to be 28 degrees. Now this angle, this direction is south, and I'm measuring west of it. West of south. So my airplane ends up traveling 37 kilometers per hour at an angle of 28 degrees west of south. Now just take a look at the last problem that we did. It turned out I started off with number 3. All of the components were horizontal and vertical. Then I used the Pythagorean theorem, step 4, to find the resultant. That's what I did. I used the Pythagorean theorem. And then step 5, I used the inverse tangent to find the angle. And that's what I did here. I used the inverse tangent to find the angle. So these problems are all very similar. Some of them are a lot more involved than the others, but they're all following these same steps. Let me take these same exact steps over to my very last problem. Step 1, look for diagonal vectors. I've got a couple of them in this case. There's a box being acted on by 3 forces. What is the net force? And in what direction is the net force? Here's my vector. One of them that's diagonal. Here's another one that's diagonal. I'm just going to copy them over here. And what I need to do, I need to find the x and the y components of each of these. So I know that this is 45 degrees, and I know that this is 30 degrees, so that means that this is 60 degrees, because this angle's 30 right there, so that means by complementary angles that's 60. Alright, let's go through it. So I'll do the sine of 45 degrees. Now there's a little shortcut if you know your way around a 45, 45, 90 triangle. You take the hypotenuse and you divide by the square root of 2 to get the legs. If you don't know that, don't worry about it. You don't need it. So then I take 10 times the sine of 45. It's okay. You know, if you do know it, it saves you time on the ACT or the SAT if you're taking it to know that you take, if you just would take the hypotenuse 10, and if you were divided by the square root of 2, it's the exact same number, 7.1. Again, since it's a 45, 45, 90 triangle, I also know that this is 7.1. I'm going to come over here. I'm going to do the sine of 60 degrees is equal to the opposite, y over the hypotenuse, 6. So I take 6 times the sine of 60. And you get 5.2. And you'd find this one using the cosine. The cosine of 60 is equal to x over 6. So then, doing that one, 6 times the cosine of 60, I already know this is going to be 3. Because on a 30, 60, 90 triangle, the short leg is always half the hypotenuse. And then to get this one over here, the long leg, you multiply by the square root of 3. So there's a few clever tricks that people will use to find their way around a 30, 60, 90 triangle, but you don't need to. Step 2. Replace the diagonal vectors with your x and y components. So I'm going to get rid of this vector, and I'm going to replace it with my x and my y component. So I think what I'll do is I'll just draw new ones in here. So I've got 7.1, and I've got 7.1. I'm going to replace this one with 3 and 5.2. That was step 2. Replace the diagonal vectors. Number 3, add all the horizontal and component vectors together. So my engineering speak, add up all the forces in the x direction, all the horizontal ones. I've got 7 minus 3 minus 7.1, because I'm going to say positive is to the right. So that comes out to be 7 minus 3 is 4. 4 minus 7.1 is going to be a negative 3.1. That's an important number. Let's add up all the forces pulling up and down. So I'm going to say up is positive. 7.1 minus 5.2. And that comes out to be 1.9. So I've just added all the horizontal and vertical components together. Step 4, use the Pythagorean theorem to find the resultant. So now I've got my box here, and my box is being pulled left and right, left at 3.1, and it's being pulled down up at 1.9. Now, a lot of people make a mistake right here. What they do is they connect those things. That is bad. Do not do that. It's being pulled up and to the left. So you have to add your vectors tip to tail, so you're being pulled up and to the left. There's my resultant. Use the Pythagorean theorem, Pythagorean theorem. 1.9 squared plus 3.1 squared equals my resultant squared. So my resultant turns out to be 3.6 newtons. The last step, use inverse tangent, step 5, to find my angle. My angle here, I'm going to call it alpha. It's the inverse tangent of 1.9. It's the opposite divided by the adjacent, 3.1. And that turns out to be 32 degrees. Now, there's no east, north, south, east, or west in this problem, so you're going to say above the negative x-axis. That's the best answer for this problem right there. You guys have stuck with me for 25 minutes. I know it's long. I know it's difficult, but I appreciate you doing your best to do this. It's not fun to go through this, which is why I put it on a video so I don't have to do it over and over. And that way you can go back. If there are parts that you missed, please go back and grab them if you missed them. But I did every single one of these problems according to these 5 simple steps. Look for diagonal vectors, break them into their x and y components, replace any diagonal vector with the x and y components, add all like terms together. Everything pulling to the right equals everything pulling to the left, everything down, everything up, compare those. When you find your last 2, use the Pythagorean theorem and then inverse tangent to kill it. Thanks a lot, and we'll see you guys in class.